This particular problem is what I call a coffee cup calorimeter with two materials. The next one is a coffee cup calorimeter, which I'm just going to abbreviate CCC, coffee cup calorimeter, with a reaction. So, and those are, from the lecture outline, the two types of equations that you have to deal with for coffee cup calorimetry. So, and when there's two materials, you write Q of material 1, which is gold in this case, equals minus Q of whatever the other material is, and the other material in this case is water, and I'm just going to abbreviate that W. And what this means is that the heat, well, let's start with this. The gold is hotter. The water is colder, so the heat given off, and heat is going to be in joules, the heat given off by the gold is equal to the heat taken in by the water. That's what this equation says. And the minus sign is only there because one is giving off heat and the other one is taking in heat. And we could actually put the minus sign on either side because the minus sign is just saying there's a difference in the direction of the heat. One's giving it off and one's taking it in. Just make sure you include the minus sign because if you forget it, wacky things happen. And by wacky things, I mean if you forget this minus sign right here, you can start with a material, two materials at 91 and 29.2 degrees, and your math will tell you that the answer is either below 29 or above 91. And one thing we know about this problem is that our final answer must be below our two initial temperatures. Our final answer must be between our two initial temperatures, and that's because they're trading energy. So they're coming to some sort of middle ground, if you will. Okay, so now we can plug in our numbers. So, and I'm just going to assume that since you've seen the lecture outline, you know how to do this. It's mass of one material, which for the gold will be 20.33 grams, times specific heat of the gold. So this is going to be the gold side, 0.129 joules per gram degree Celsius, times the temperature change, which is going to be T final, and T final is our unknown here. T final minus T initial, and then it's going to be mass of water times our specific heat of our water, our specific heat capacity, if you will. And it turns out that that number is on our conversion and equation sheet, 4.184 joules per gram degree Celsius. You'll notice this is for the liquid. In future chapters, we'll talk about the specific heat capacity of the gas phase for H2O and the solid phase. So we have some more work with H2O, but for now, 4.184 joule per gram degree Celsius. And this is supposed to go, I need more paper, but I'm out, so I will create more paper. And I used to play soccer, and my soccer coach would always say, create space when you're playing soccer. And so I'm going to create some space on this next page. All right, so T final, still are unknown. And T initial for our water is 29.2 degrees. So create space, but now you can't see it. There we go. Everything in this equation is known except TF. And what I'm telling you, and when all temperature changes are complete and the final temperature of the pure gold and pure water are equal, so TF is the same number. And so there's only one unknown and one, and now we can solve for it. So the only thing that's left is algebra. So now I'm going to multiply these two together and then distribute on this side. So 20.33 times 0.129. I get 2.62, which is going to be times TF. And so you can also just call TF X if you'd prefer. But I'm going to leave it as T final, TF. And then it's also 2.62 times 91. And I get 239 is equal to minus these two numbers multiplied together, 58.4 times 4.184. I get 244. And now I will distribute it between both of these. So it's going to be 244 T sub F. And now I have a minus and another minus, so that's going to be a plus. Sorry, 58.4 times 4.184 times 29.2. I get 7135, like so. And I have abandoned my units here temporarily. Hopefully that's okay. I'm happy to discuss units if you'd like. But now I have two numbers that have TF in them. I'm going to bring the minus 244 TF over to the left-hand side and add it to the 2.62. That's a number times TF. I'm going to take the 239, add it to both sides, so I will add it to the 7135. I get 7374. And now I've made all my terms positive. And now I just have to divide through both sides by the 246.62, which is probably way too many sig figs, but we'll go with it. And I get 29.9 as my answer. And since it's a temperature, and since all my temperatures are in degrees Celsius, I can show that that is the proper set of units. And that is our final answer, 29.9. And just, again, one other thing we know, by the way, if we look at this problem, is that since the specific heat capacity of water is so much greater than the specific heat capacity of gold. It's like, well, let me see, 4.184 divided by 0.129. It's like 32 times bigger. What that means, so much greater than C sub S AU. What that means is that T final, it takes so much more energy to change the temperature of water. That's what this specific heat capacity term means. So much more energy to change the temperature of water that the final temperature must be much closer to 29.2 than 91. So T final must be closer to the initial temp of the water. And I say that two of these things, this one in red and our other statement about our final answer or final temp must be between our two initial temps, because it is so easy to mess up the math on these. And if you have an idea about what your answer should be, then that's going to help you make sure you do these problems right. Any questions about this problem?